Oh, yes, there we are live at 2 seconds. Excellent. And hello, everyone. It's like, it looks like there's at least 3 or 4 people have shown up, so that's always a good sign.
Yep.
So we have Paul Anderson.
Wrong Paul.
Yeah, the wrong Paul. As my moderator here, Paul, he's going to try to manage the questions for me, and I think there's already been some really nice comments in there. The best one being from Jesper, just saying hello. Hello, Jesper. It's good to hear from you. And also from Charlie. And Charlie, you're absolutely correct. That is absolutely the best way to solve any performance issue. Cool. So we're here to look at what I call the performance anti-pattern revolving door. And we just have a bit of time to actually go through this interesting phenomena that I found. And I, normally I've been speaking a lot about memory and memory issues because memory is, it can have a really significant impact on the performance of your application in some extremely bizarre ways that you wouldn't actually even expect. And we've already had some interesting talks just from Peter Lowry. I just watched his talk. One I'd recommend to go back and take a look at if you haven't. He's talking about, well, quite a bit of his talk is around zero allocations in the JVM, which is an extremely interesting topic. And there's some really interesting performance improvements that can come from these type of techniques, or the type of techniques that Peter's been developing for years now. And I guess the other related talks to some of the things that I'm doing here are the talks on Loom. So Dr. Heinz Kibbutz just gave an excellent talk earlier on Project Loom. And I think on Monday, I don't know what time, sometime 8 a.m. Pacific. It probably doesn't matter depending on which time zone you're in. But anyways, it's another talk on Project Loom from someone who has a lot of experience with React. So here's two extremely well-versed people in the world of concurrency that are sharing their experiences with Loom. So that's really cool. So pop into the chat there, pop in some messages, say hello, let us know where you're from. I see Jorn's already made some comments there to hello Jorn. And let's get on with
so Kirk, if I can jump in here for a second.
Sure.
For some of the folks here that haven't been with Kirk before, on behalf of the Java Champions Conference, I want to welcome everybody. Kirk Pepperdine from Microsoft will be doing this talk on the revolving door pattern, and Kirk's going to take questions as they come in the chat. So feel free to jump in, and we're looking forward to learning a lot about virtualization and performance with the JVM from Kirk. And for those of you that are here for the first time, I guarantee you'll learn a lot. Kirk is very knowledgeable, and it's I've known Kirk for quite a while. It's always a joy to work with him and to have this happen. So I'll be back in a little bit later then, and enjoy the talk.
Cool. Thanks, Paul. Okay. Paul spilled the beans on all this stuff, so I'm not going to really go through it. Let's just get to the good stuff. Now, the first thing I want to talk about was like anti-patterns, and I think a lot of us are familiar with the lingo of design patterns and patterns in software development. But just as a quick review, I thought I would just show a small diagram here to help people remind people exactly, what it is we're talking about when we're talking about a design pattern. And really what we're seeing is that, in software, we're always faced with some problem or some business domain thing that we need to come up with some solution for. It's these contexts and this context and these forces that help shape our solutions to these particular problems. And of course, with any solution, there's going to be benefits and consequences, and probably alternate paths that we could have taken. Right. And if we keep seeing this thing happening over and over again, then what we can do is we can generalize this, and we would generalize this out into what's known as the design pattern. And you can see there's plop is one way that we can use to describe these things. And so we can come up with things like command pattern or flyweight or factory or something like this, and we can just say that, and it gives us a very concise way of describing some of our designs. Now, just as there are design patterns, right, sorry, getting into this one here, it was like, one of the first books on design patterns, and there's many more, and I think Dr. Heinz Kubitz has a number of talks out there on design patterns, and they're all really good. Anyways, so just as we get into patterns, we also have anti-patterns. So these are what I call a reusable template for a solution to a commonly occurring design problem. But instead of giving you positive consequences, these things generally give you negative consequences. And it's very strange because these might be like widely accepted ways of doing something where people don't actually or haven't really realized the negative consequences to employing these particular design choices into their applications. And really, the anti-pattern template follows what we see with a pattern template. So we're going to describe the general form, primary causes, symptoms, consequences. But unlike the pattern template, what we're going to do with this one is that we're going to suggest a refactoring or an alternate pattern that we can use that would lead to a better outcome. And so you can see a bit of a flow chart here, right? So we have a solution, and in this case, what we're saying is that people are actually taking a design pattern, and what they're doing is they're applying it into a new context. And in this case, they're transforming a pattern into an anti-pattern. And there's going to be some symptoms and consequences here. And the refactored solution should be applying an appropriate design pattern for that context and the forces that you're dealing with. Right. So so it's kind of nice to recognize these things so that when you look at something like, for instance, I think I used a DTO as an example of this. Now, if you look at the history of DTO, it was really to solve what's known as what we call a revolving door problem. And this revolving door problem comes with what I call like bursts of very short calls across the network to get data. So you basically have an entity bean or session bean or something like that. And that bean was not serializable. So you just couldn't grab the whole thing and pull it across the wire. So you do like get. And consequently, you just have these like very small, numerous small underutilized packets that required very small amounts of processing. And this was a real problem. Yeah. So speaking of revolving door, just for fun, I thought I'd, explore where this came from. And so here it is. You look it up and you say it's invented by this guy, the Theophilus Van Canal, I guess, in 1888. So really hasn't been around for that long. Became very stylish, I guess, in the 20s to have revolving doors on your building. And of course, there's been lots of benefits. Now, if you look around, the fun part is that the thinking was that it was to prevent horses from entering the building, to use a revolving door. Now, I'm not sure that horses like going through any small door, so I was kind of suspicious of this. And when you actually do a deeper dig, then it's like you find that Theophilus didn't like holding doors open for women, which was, of course, the etiquette and practice for the day. And it turns out there's a lot of benefits for it besides getting rid of this quote unquote social burden. if you want to call it that. It's fantastic for energy consumption, helps moderate foot traffic, and it feels like a good design pattern. And in under the right circumstances, it actually is, because in this case you get the energy conservation and moderating um, uh, foot traffic. Now there are some things that we can actually learn from that we can take into the computing world from this example, which are actually positive benefits in this case. So so if we think of the door as a shared resource, that means that basically one person can go through it at a time, and which means that you hold that resource for a fixed period of time, and that's essentially like a single threading of the flow through from one place to another, which is what we're trying to what's being controlled here, right? So and strangely enough, we can now apply some mathematics to understand the throughput of people through a door, and that's just basically throughput is equal to 1 divided by the amount of time it takes a single person to run through the door. Now, if we're pipelined in one direction, then that's generally pretty good, because then everybody takes a constant time to get through the door, and you line up and you go through. But if we have a bidirectional flow, then all of a sudden we have a problem, because now 2 people arrive at the door, and you have to communicate with each other to figure out who's going to go first, and hence there's probably some social etiquette and whatnot around there. I know my friend Andras always has a joke, which I won't repeat here, about how I guess it's called a Canadian standoff. It's like after you type thing. Anyways, but the extra cooperation increases service time, which basically decreases the throughput. And so a solution, to this particular problem is, if you need to get people in and out, is to put in a revolving door, because you just have, people going in on one flow and coming out the other flow. So it reduces the need for extra cooperation in the system. Now, it still creates a bottleneck in your system, but at least it alleviates some of the congestion that you might have with the shared resource. So, so this is actually a good use of this resource. But you generally have to think about, okay, well, it's not just this barrier that I have to transfer. It's like, what am I doing, and how am I impacting the other resources? And this gets into, I guess, going back to the computing world, just having to come up with some definitions so that, as I use these terms, we have a shared understanding of them. So if we look at Thread Scheduler, right, it's a piece of software in the operating system that's designed to figure out, what needs to be done, and then fill the task queues of the CPU, right, and give them some time quantum that they can hold onto the CPU, and they just, so their job is really to keep the task queues full, so everybody gets a fair share of the CPU, for some definition of fair share. So we're going to use some heuristics to figure out how to do all that, and what the time slices look like, and everything like that. So yeah, so there's a couple of things that can happen here. You could use as a thread, I can use my entire time quantum, and when I do that, I'm going to be interrupted, and then I'm going to be kicked out, and I'm going to be replaced with something else. And so I go back into the thread scheduling queue, and the thread scheduler will reschedule me for some time in the future. This is known as an involuntary context switch. In other words, I didn't ask for this, it just happened to me. With a voluntary context switch, my system has crashed. What is with this? I need to reboot. I'm backstage. And I'm in the show. Am I in the show?
Yeah. Hey, Kirk, welcome back.
Yay! I
We're
made it
both,
back.
I guess we really are in a revolving door here, huh?
No kidding. I just put my hand on my machine. I realized I could like roast my dinner on it. It's
Yeah,
like
that's what you
got so
said.
hot.
Wow.
I had no idea. What's happening here? I'm going to
Uh,
share my screen
Yeah,
again,
share your
and let's
screen
see if
and
we can get
I'll
going
get it
here.
right. Yeah, share it and I'll get it right back up for you. Okay.
Okay. Are we live? We should be live.
Yeah, we're fine.
Okay. Awesome. That's fun. Okay.
Okay, there we are.
That was a hard crash. That doesn't happen very often, I'll tell you. So where were we? Oh yeah, I was talking about voluntary and involuntary context switching. I'm just going to keep this show down to a minimum here, and there we go.
Okay.
So yeah, involuntary context switching, voluntary context switching, voluntary context switching is I'm doing something, I'm going to stall, and that's going to cause the thread to yield the processor to the next task in the queue. So these concepts will become important as we progress through what's happening here. So if we look at the revolving door anti-pattern, what our intent is here is like we're going to drag data over a barrier, and as we go over that barrier, we're going to trigger involuntary context switch. So what I mean by a barrier, it might be a network barrier, it might be some sort of lock thing, but something that says I can't make forward progress here. So, and it's very likely I'm not going to make forward progress for a long time. So I'm going to get evicted from the CPU or from the core, and somebody else is going to come in and then soak up those cycles doing something useful. So, the thread scheduler is really there to keep the system, the entire system making forward progress. Right. Okay. Yeah. So a lot of this was actually done with early, what do you call JEE servers, Jakarta, whatever you call them today. I'm not sure. But in particular EJB, because again, we ended up doing these very low circular patterns. But this is not the only place where it's showing up in quite a few other places, as it turns out. Yeah, so calculation engaged in a large number of high tail latencies calls. So that's what happens is that your tail latency picture all of a sudden becomes your normal picture. Right, no one uses OR mapping tools, and actually microservices is a place where we're seeing this show up. We've seen it show up in gaming and a few other places. Summary solutions is to somehow bulk up your data source, and again, this depends on the context you're in. If you can, if you're able to do this, or possibly not, maybe you have to go to a different solution. So let's take a look at a couple of case studies here. And I've completely lost track of my timing now from the whole thing. Yeah, okay, we're good. So case study. So service is performing poorly, and we go and talk to the client, and the client says, yeah, well, we had the service and we didn't know what to do with it because it was not stable, and there was lots of jitter and all kinds of performance issues with it. And we figured, what, there's probably something to do with the garbage collector. So what I'm going to do is I'm going to just increase the heap size and redeploy that way. So they increase the heap size, redeploy, and boom, they're all of the problems magically go away. And they get much better performance, they get much better stability. They don't have any of the stalling issues that they had before. So they're creating all the jitter and everything for the end user experience. But the consequence of this particular solution was all of a sudden their costs went up dramatically, right? Right, because of the increased memory footprint. So it's all cloud-based, and of course, memory footprint is also one of the drivers of costs in the cloud. And right, so what we were not told, and these are always the fun bits, right? So you come in and you look at it and say, okay, so what does the environment look like? What did it look like? And we found like, oh, they increased the memory footprint, but since they had a fixed size server to work with, that meant that they needed they put fewer virtual machines on the server, but they had to have more servers, obviously, right? So that's what caused the increase in COGS, right? So the next step is let's go try to get some measurements, see what's going on in the system. So we start with first principles. Is we want to look at what the hardware is facing in this environment. And so we got a originally configured virtual machine app. We start running the app, and we start having fun with it and everything like that. And boom, all of a sudden, we just get these numbers. And these are really raw, seemingly meaningless numbers about just got gathered with VMstat, just performance counters we just gathered from the operating system. But even in here, you can see some really interesting trends or things that are quite interesting. Let's see if we can walk through them, right? First, if you look at the idle, it appears as if the server isn't overly busy, right? It's like 60, 70% idle, and you're going, okay, well, in that case, you have to ask, okay, so how come we're so idle? Because if you look at the runnable queue over on the left-hand side, we have quite a few threads that are ready to run, and we got plenty of CPU there to let them run in terms of idle time. And so the question is, what's going on here? How come I can't get these runnable threads into a CPU? And if you look down over here at these two columns, you see so I'm looking at a breakdown of my threads, or the threads that I have running. Okay, how much time did they spend in user space as opposed to how much time did they spend in kernel space? And you look at it, it's like, okay, 26.4, 26.5. And, those numbers might not mean much to you now, but to me, they actually meant quite a bit, because what it said was that with very little activity on the server, I'm actually driving a lot of load on the kernel, relatively speaking, right? And furthermore, if we look at this particular slide here, we're looking at it going like, okay, so this is what we're actually doing. We're driving context switching rates up. And of course, the thread scheduler is an OS level activity, which means it's going to get tagged in the system column of time. So it's very likely that what's driving up system kernel times here, and actually consequently driving up idle time, is the rate of context switching, right? Now here's the interesting one. This was the real kicker, because everyone was scratching their head over this one, right? We logged all the users out of the system, so we let the server go idle. And once the server went idle, then you can see the context switching rates actually went up. And you're going, okay, what's up with that, right? And you can see that the context switching rates went up, and the system time remained relative. Of course, user time is going to drop, which really means that ratio from user time to system time is it's much more pronounced in this particular case. Yeah. So the question is what's happening here, and you can see all the clues have to do with what's happening with context switching in the system. We get into case study 2, and I look at this one. This is a completely different app. It's a simple web app, and this is actually a case study that I keep using over and over, because there's a multitude of problems in this particular project, and so some of you might be familiar with some of the graphics if you've seen them before. But this was deployed on a Windows system. The other one's on Linux, so you can see that there's really no difference between operating systems in this case. But again, we're in a situation where we have a 3-tier application. So it's web app to an app server, browser, web app, database. So nothing spectacularly interesting about that. Typical user load is about 10, 12 users. It's an internal application for a company. They just don't have many people using it. And what they're doing is like they're scheduling shifts for people. I guess it's all, some of it had to be manual because of, I don't know, complications or whatever. Details really somewhat unimportant, but the database performance in this case here is like sub-millisecond. It's really, really good, right? Network is lightly saturated. And if we look at the CPU stats here, you can see that, we have really the kernel, again, being hammered. That's the bits in red. And really, if we subtract the red from the green, then you'll see what the user time is, right? So again, there's what I call very, very little user activity here, just producing a ton of load on the kernel. And in this case, you can see that it's also has an issue where there's just a percentage of the CPU that's never reachable simply because of the runtime conditions inside the hardware, and that's an issue here, right? Yeah. So and again, these people were seeing like response times that were incredibly long. I forget the exact number, but certainly longer than a minute or something like that for what ostensibly should be and eventually was something that took less than a second to complete. And so at first everyone was sort of like blaming the database and things like that, but as you can see, the information coming from here is that the database is performing well, the network is performing well, there's no problems in that part. So this is actually a case of the service provider is providing the service in a very timely manner, but the consumer is somehow messing up the game here, right? So in this case, we're going to look at the consumer of the information coming from the database and try to figure out, okay, what are the conditions that you're consuming this, so that we can understand what's going on. Now, again, you can see that the ratio here is about 40% of user kernel time here. It's like really, really high. Now, I have a finger in the wind estimate of about 10% for being my what I call allowable ratio of pressure on the kernel by the user code. As soon as you start getting above 10%, in most cases, that's going to be an issue, simply because you're putting excessive pressure on the OS, and we have to think about what is the OS there to do for us? Well, one of the things it's there to do for us is to manage non-shareable resources. The key word, the key phrase in there is non-shareable. And as soon as you hear non-shareable, that should bring up, a whole bunch of red lights in terms of the, how does this affect scalability of things? And as you can see, it just has a terrible effect on the scalability of things because, your AMDL is going to hit you really hard at this point in time. And in this case, you run into this very nice situation where as I apply more threads to try to soak up the CPU, I'm going to make the problem worse, right? So, and that actually probably gives you a hint as to why in the first case, when they reduced the number of servers on or machines on virtual machines on the server, that things got better, right? Yeah. So, what do 1 and 2 have in common? Well, they have this really high kernel to user ratio. Our computers and software use for sure. Yeah. Right. I was just going through the comments. If people want to make comments, certainly we'll try to address them as soon as we can. Right. So yeah. So in the Windows case, we had 40%. With the other server under load, we had 20%, 25% when we take the load off of the server. So like I said before, that actually makes things get much worse. Yeah. Now, yeah. So why is 10% of users considered high kernel threshold? I think I just covered all of that, and I think if people are not aware of AMDL's law, which I'm sure most people are nowadays, then that any point of serialization in your workflow is going to decrease your ability to parallelize your workload. If you have multiple cores on a machine, then of course that's going to affect your ability to utilize all of those cores. Right. So the question is, what is being asked to do and how much does it cost? That's another question that we want to try to answer in this case. And, what does Little have to say about this? And then, with that, we need to go back to looking at, why did the context switching rates go up on an unloaded server as to where they were on an unloaded server? And, the sort of interesting questions. And it really comes down to, I think, if you look at the hints in the data, it's clearly to me suggesting that context switching is at the root of the problem. And what we're suffering from is high rates of voluntary context switching. Now, so how does, so why did the rate go up when when we took the workload off of the system? Well, you'd have to think of it this way. It's like if I have an event loop and the event loop is running hot, and in other words, it's just spinning, trying to pick up events and things like that. If it has to do any amount of processing, that's work. If you throw that into Little's law, it basically says, well, the time I normally take if I'm idle, or just spinning, plus some work, means I'm going to get lower throughput, which is in effect putting load on the processor, which is going to have this other effect on context switching rates, which is going to effectively lower them because the threads are actually spending more time in the CPU than they otherwise would be. So when I take the load off, they're not doing anything, then I'm just going to get a situation where I'm context switching with very little, if no work at all. And of course, that's going to drive the context switching rates higher. So just a little bit of background on queuing theory can really help you reason through some of these situations to help you make sense of them. Right. So if we get back to case one, I think you'd have to ask the question, okay, so why did taking services off the system actually reduce the problem? Well, it actually didn't have anything to do with the memory that they added. What it had to do with, since I took, I cut the number of processes down from I forget what it was, 8 or 6 or something like that to 4 or 3 something. So I cut them in half. All of a sudden, I'm just putting less load on the thread scheduler, right? So if we look at what the thread scheduler is doing, it's, so dividing CPU cycles, it's a fairly complex problem. There's a nice paper out there I referenced at the end, which is called a decade of wasted cores, which looks at the efficiencies or inefficiencies within thread scheduling. And recently Linux has gone through a number of changes, and these have rippled through other operating systems, but they wanted to have some sort of fair share, so they've had to go to more complex schemes to introduce some fair sharing and everything like that. The point is, the thread scheduling itself is a complex task, and is optimized as it is, it still takes time, and you still have to run. And if you have a lot of these very short-lived tasks that voluntarily context switch themselves out of the processor, you could leave yourself in a condition where your task queues are simply empty. And the only way they're going to get filled is have the thread scheduler run them again, right? And there's all kinds of harmonics and things in the system that might interfere with that also, which is it's kind of a very complex environment to run in, because for instance, if you're bound to run on core 0 and core 0 is busy, you're not running on core 0. You have to wait until your turn until you can run again. Meanwhile, all of your other cores are going to be left effectively idle. Let's see. So lots of words on slides for people who might want to read this afterwards, but effectively, I think we've covered most of this here. So case study 1, servers receiving many small requests, hyperactivates the thread scheduler, heats up the kernel, leaves cores idle. Log case has smaller unit of work, so that it burns through the cores faster, and that heats things up a little bit in terms of context switching. Right, and this is really what I call an example of what I call a revolving door anti-pattern. It's like, I'm dragging data through this barrier, and we're just doing something very quickly, and we're just spinning here. And at that point in time, managing the work becomes more costly than actually doing the work. And I think it's one of the key points here is that is that the threads the act of scheduling threads now actually becomes a process that's in every single application's critical path that's running on that piece of hardware. And I don't think that's something people consider. So that means that the rate at which you have one application context switching at will affect all of the other applications that are running on that machine. So this is like an accumulative effect across that piece of hardware. So in this case, this led to the situation where they added more memory, they offload, they reduce the load on the thread scheduler. Of course, you release the pressure on the bottleneck, you're going to get much better performance. It turns out the memory was provisioned about 4x of what was needed. And so the solution in this particular case was to say, okay, well, let's just buy many more much smaller machines. And to give you an idea about how entrenched some people can get into some ideas, and this is not just for this team. I've seen it happen in many, many other teams also. As soon as they recognize that, hey, we could reduce the memory footprint of our virtual machines, their first response was, oh, that means that we can put more virtual machines on a piece of hardware. And, the answer to that was like, no, actually, we can't. You need smaller hardware because what you're trying to do is take the pressure off the thread scheduler. So, really trying to understand the resource that's under pressure is really helpful in helping you understand what it is that you need to do in order to take pressure off of that resource. In this case, study 2 had many, many calls to the database basically were performing an in-memory join in Java, which, as you know, is a horrible thing to do. The database and network were they were just able to manage this very nicely. But we basically had thread spinning over the network interface, which means that they're dealing with a non-shareable resource, which is like the buffers on the network card. So there's locks down that path, and you have to wait, and because of that, you get these high rates of voluntary context switching happening as you were trying to push these small packets of data out to the database and get back these, again, trivially small packets and then process them. So you're just basically, again, spinning over this resource, which is, I guess, another example of a revolving door anti-pattern in this case. Right. Oh, it looks like I went through fast even with the crash. I think the crash caused me to hurry up and probably went through too faster than I should have. But anyways, the conclusion is the source of the performance regression in both cases was like high rates of voluntary context switching. And as I mentioned before, the thread scheduler being a shared resource in the system, we have to consider, the aggregate impact of all of our applications' impact on this particular resource when we're analyzing for problems in our system. And the other thing too is, like, we were in a lot of virtualized environments before. We just have to recognize that hypervisors cooperate with the thread schedulers, so they actually increase the amount of work that the scheduler has to do, because they now have to cooperate with the hypervisor, to get the work done. And of course, more work equals longer service times equals hotter kernel, and that can have some negative effects on your applications. Yeah, and that's a really good question. So conclusion, revolving door patterns work will inflate the involuntary context switching arrays, place thread scheduler into. So the thread scheduling is really set up to be predictive. So it's trying to predict as to when it should be running next, and it tries to schedule itself as such. And if you have a lot of voluntary context switching at a very high rate, then it actually places in the scheduler into this react mode. And if you're reacting, you can't keep up, right? And that's really the problem here. So cooling down the rates of context switching is actually what you want to aim for. And some ways we can do that is to bulk up the size of the units of work that we're working on. So instead of working on individual events, maybe we can queue a bunch of them and then send them forward. So again, you'd have to look at the latency concerns, because of course, if you queue things, you're injecting latency into your response times. But you might actually make up for that little bit of latency, but induced by queuing, by simply being able to get through the unit of work faster, because it's less interrupted by all of this context switching activity. Again, the solution is really going to depend upon your situation. So futures, there's Project Loom, which I've given a shout out to for the talks here. I don't know if Project Loom is going to help in this situation or not. One can hope that there are certain situations where, where Loom would come in and basically, by using virtual threads, be able to bulk up the activity of many virtual threads onto a native thread. And in that case, we should be able to slow down the rate of context switching on the native thread. But then, of course, the obvious cost there is, what does it cost to use Loom? So this is actually one of the things that you might want to look at. I guess I could talk about continuations. Again, these are models for asynchronous programming to help you basically not have one native thread per call. So that because if you traditionally, we've had one native thread per call, and that native thread has spent a lot of its life just basically blocked. So we can look at other techniques, I guess, that can actually help us take that quote unquote block thread and unblock it and have it do other useful work for us, so that we can, again, from a global perspective, keep the system making good forward progress. So I've mentioned these talks. There's a URL. You can do a good search on YouTube and find it also. That's for Thomas and Heinz. And the Decade of Wasted Cores was actually published by the University of British Columbia. And there's cross collaboration, I think, with some of the universities in France also. So it's a very interesting read if you want to read more about thread scheduling to get a better understanding of it. And there's other resources I could have put in here for that. Anyways, so that's pretty much all I'm going to say about this topic today. Sorry for the crash. And I guess what I'll do is I'll flip over to questions now. And so what can you do with systems like Kubernetes or PCF, in which you have a set of big servers and then a lot of containers competing for resources? Yeah. So I think I think the whole idea behind, well, not the whole idea. I mean, one of the ideas behind Kubernetes and Docker and all, and a lot of the virtualization techniques was ease of administration, and also there's all kinds of other different advantages that we're all well aware of for using containers. I think one of the ideas or notions that was promoted by the pundits early on was this idea that we could get better saturation of our CPUs, of our cores, and in some cases, I think that that's possible, but a computer is more than a CPU. There's all kinds of other machinery in there that we're dependent upon in order to get our workload completed, to work through the tasks that we need to get done. And we need to really understand what is it that our application is truly bottlenecked on? What is the resource that we're actually putting pressure on? And I think if you look at the problem that way, then you can come up with a reasonable solution that makes sense for for your environment. Like I said, for our first case study, really, they are running in Kubernetes, and in that case, this was a real question. It's like, how do we repartition our application or redeploy our application in some way that makes sense? And in that case, it made sense to go with many more smaller machines. From a cost perspective, it actually worked out to be cheaper. That was the solution in that particular case. In some cases, you're perfectly fine on a big machine. Really, really fine on a big machine. I think just recently what we've seen is a newer trend to reducing memory footprint. So everybody's trying to go with as small a memory footprint as they possibly can get. One of our guys internally did some study with Kubernetes deployables. I think they found I think New Relic actually did a survey, and they found that the vast majority, I forget the exact number again, but it was stunningly high, like 80, 70, 80% or something like that. The vast majority of Kubernetes deployments are constrained to about 2 gigs of RAM. So they're really, really, really super small deployments. And, in this case, as people work forward and try to reduce memory footprint, I think sometimes we get into this case where we have wishful thinking, right? We hope and think that wish our application could run in 2 gigs of RAM, and maybe it can, and maybe it can't, but you really have to look at the hardware requirements of your application. You have to understand in a production environment where the pressure point is, and maybe this is an application that a node runs perfectly well on its own, and you don't really see a good pressure point. But then you have to look at it from the perspective that, I'm going to ramp this up, and I'm going to have, I don't know, dozens, if not hundreds, of these things running, or well, definitely dozens of these things running. So what's the aggregate effect of having all of these virtual machines running on the same piece of hardware? And that's one of the things that you're going to have to study in your system to sort it out. But I think the key point is like trying to understand what is the resource that's under pressure. And quite often we find that the current tooling looks at what's happening within an individual JVM, or if we look at OTel or something like that, it's looking at what's happening as I trace this thing, this activity as it's running from left to right through your system and back again. And really what we're hoping for is tools that will give you a better, more holistic view of the system, so that you can understand what's happening in aggregate, because that view is extremely important in answering this question. Too many native threads kill the scheduler. Loom might give, too many native threads kill the scheduler. I'm not, Jesper, it's really funny thing here, because people, I'm not saying you have this view, but I have come into many people who will say that because I have more threads, I have more context switching. And that's that's not actually what's driving the context switching behavior. What's driving the context switching behavior is the rates of voluntary and involuntary context switching, right? And also, to know in modern thread scheduling systems that the the time quantums are not fixed. They're adaptive to what the system is seeing in terms of like how much of the time quantums are being consumed. And again, this is to try to get the thread scheduler into a situation where it's being more predictive, and of course to give you better better utilization of the CPU by real work as opposed to this housekeeping work. Try to rebalance that. So that's really what's driving context switching rates, and I'm not sure that the number of threads has much influence on that. Now, it will drive up costs because if you have 100 threads or 1,000 threads, you do have to manage those threads. Now, with the unfair thread schedulers, you had order one thread scheduling costs. And that's now gone with the fair share thread schedulers. So we now have like basically, we have a tree structure, and there's a balanced tree structure that helps sort of which threads should run when and for how long they should run. And of course, it's more expensive to maintain that tree. I think it's more like n log n. Right. Let's see. Is there anything else in here that I've missed? Do you see anything else, Paul? We're gonna have Paul join us, actually.
Yeah, I'm back here.
Here we are.
There's all very interesting discussions here. Anybody else have any questions for Kirk about maybe some things that you're seeing on your systems or some issues that you're dealing with?
Yes, there is a. Oh, Mary is talking about she was stuck in a revolving door. Something? I don't know.
I think we've all done that.
Or you like the new ones where they just automatically go around and by themselves, and if you get too close to the leading edge, it suddenly decides to stop for whatever reason. Yeah, there's really kind of some fun things in there. Right.
Yeah, so Kirk, I thought of something. There's undoubtedly some people here that probably are wondering how you get all this expertise and how you are so informed on some of these issues, because this is clearly your expertise and everything in this area is something you don't pick up in textbooks or take regular college courses for. So for people that have to really look at some of these issues for performance and everything, do you have any suggestions or guidelines about how you can get more expertise in this area, maybe in terms of blogs that you read or other types of resources?
Yeah. No one gets there by themselves. Absolutely. So there are, I guess, so many different people that we've had, I've had the privilege of having direct conversations with, and just sorting through things. I think I think the first thing is just being curious and really trying to dig in to figure out why things work. And I know that that's one of the things that Heinz does quite a bit, and you see that in his newsletters a lot, where he's like digs into something and just like, how does this thing really work? What's really going on here? And then once you think have it challenged by someone else. Give it to someone else to look at it and have them challenge what you're what you're looking at, to see if it really is what you're looking at, or having this different perspective or idea about what potentially could be going on. Because a lot of these systems are complex and the interactions are very complex. So I think that's a couple of steps. Yeah, Jesper says experience. Well, you gain the experience by doing. It's like when we first started running benchmarks, I mean, again, there's people on the list that will laugh because they'll say, yeah, our benchmarks were really, really bad. We're doing all of the wrong things. And it was really by showing it to someone else, they'd look at it like, did you realize? And then go like, oh no. And it's like, and eventually you start accumulating all of this information. Of course, reading blogs. There's two, I'd hate to leave someone out. So I'm not really going to list them, but there's quite a few blogs that are quite good. There's there's a lot of resources, I think, in terms of performance tuning. Like I should mention, where is it here? Just a second. This book, actually, can we see? Do I get my camera on properly?
Oh yes, that's a good one.
Yeah, it's really, and these guys have done the same thing. They've gone around, they've talked to a bunch of people, and they've drawn a lot of experience from different people, benching everything. Just be curious, and they actually wrote it out into a really really nice resource. So I think just paying attention to these and just benching and. I think a lot of people today will just take a benchmark and they'll just wrap it in JMH and just let it run, and they'll take the numbers and say, there's my answer. And to me, really, that's just the first step, right? That's just the beginning. That's not the end.
Are there any public domain tools out there that you would recommend or that you like to help you study systems and try and make sense out of what's happening?
No, that's if you go to javaperformancetuning.com, Jack Shirazi has basically listed as many performance tools as he could or felt like listing. After a while, it just gets too numerous. To me, it's really well, you can see we solved like this really hard problem just by looking at VMstat initially, right? So some of the tools are very simple. Looking at perf, I think anything that's giving me a hardware view as to what's going on to me is very important because it's the conditions in the hardware that are going to determine whether your application is going to run fast or not. I mean, of course, it's also how you've coded it, but even if it's well coded and you get laid out incorrectly in memory, I mean, that could be a 40-60% performance hit, right? Just by how you get laid out in memory. So if you just get laid out across, basically one of the important barriers, like, code cache boundaries, I guess cache lines, then, you could be ping-ponging, looking for code all the time, trying to cross these barriers, which are expensive. And there's other things. We've run into apps that were well written. They just got deployed in the cloud against something that wasn't so nicely written.
Right.
And the only way we got to that is, well, we used proxy measures in those cases because we couldn't get measures directly because the cloud providers wouldn't allow us. So we just gave them a threat. Said, okay, you have to give us access, or we're just going to move to another provider. Then we get access. But quite honestly, and when we saw that, I was like, oh, okay, now you need to isolate us from these things, right? So it's like the noisy neighbor issue. But essentially, we spotted it using proxy measures, and I think to use some of these proxy measures, it takes a little bit of experience and understanding as to what's going on, and I guess a bit of conjecture, right? Although I'd like to rely less on conjecture and more on some direct measure.
Good. Okay, so do we have any more questions for Kirk here? Because we're coming up on the hour time here.
And I think we're done. Thank you all for attending and staying to the end. And yeah, thank you, Paul, for moderating.
Yeah, thanks for the great talk, Kirk, and thank you for all coming. Enjoy the rest of the conference, and we'll see you hopefully in person at some point.
Yeah, we have to thank Ken for setting up this wonderful event.
And thanks to Ken. Yeah, Ken did a great job on all this.
Yeah, absolutely. Right.
Okay, have a great day, and I'm going to sign and end the broadcast here.
Thanks all. Bye.